Thanks. I thought I'd just start by just talking a little bit about who I am. So my background is in science, in neuroscience, in academia. I did that for some years, and then about 10 years ago, I started working on neuroinformatics, which is about using computers to deal with neuroscience data, still within academia. And then about 5 years ago, I left academia and started working on a number of commercial projects. The only one that's still around is Optonomic, and it's actually a really cool project. And I think we've done a very good job of marketing this within the Haskell community. So we've used Haskell to build an app store for mental health care, in particular for addiction treatment clinics. Where clinics can activate modules corresponding to different diagnostic tests, some of which tell them if the patients are getting better, sometimes communicating with the patient through the smartphone, and some of it to deal with regulatory compliance purposes. And this is still going on, and if anyone is interested in mental health care and using Haskell for that, if you feel that you need mental health care because of the Haskell type checker, then get in touch with Beat at Optonomic GmbH. Then 2 years ago, I became the chief data scientist at Beautiful Destinations, which is a creative social agency that works with travel brands around the world. And we had a lot of data science challenges, building algorithms to predict whether images would be liked on social media, and several people here worked with me on that. And then about 6 months ago, I left to set up a company with 2 friends where we are delivering institutional level risk management solutions to private individuals. And in addition, I work with Tweak, and I'm working on an open source data science stack in Haskell that I call diffusion kinetics. So this is to say that everything I'm going to say in this talk is biased towards being a scientist and working with predictive analytics to solve problems. And that might be very different from other data scientists. So what is data science? Okay, so I'm going to offer my definition of data science. And that is that a data scientist studies the behavior of a digitally connected network of humans. And by saying that, I've just made a lot of people very angry, I think. I probably violated the code of conduct. And that's because a lot of data science is often about tools. And I apologize because this is also yet another talk about tools in data science. But I think we shouldn't forget that data science is as much about tools as particle physics is about cloud chambers and cyclotrons. Yeah? So we're actually studying something in data science. So I actually make no apology for insisting that data science at the end of the day is about learning something about something, not about installing Hadoop. I feel considerably worse about disappointing the people who work in physics, maybe in ecology, who feel they're data scientists and don't work on humans. But just looking back at the classical cases of data science, which a lot of data science come from marketing, public health, public utilization of resources, business operations. Often what we do study is people. What they like, what they want, what they're afraid of, whether they're sick, how they sleep, and sometimes with whom. And that's the kind of questions that we've been working at in data science for a long time. So let's talk about the data science process. So you start off with trying to get some data. And sometimes you just have some data. Sometimes you get it from an external API, linking to data sets maybe. Sometimes you have to go out and get your data. You have to run an experiment. And actually that's both as a scientist and a data scientist, that's more been my experience, that we've had to go out and get the data. And then you have some data that's somewhere in a database typically, or in a spreadsheet, or in a spreadsheet file. And then you often have to take a step and clean that data and tidy it up. Cleaning means trying to remove errors, making sure the data set is complete, or that you're working maybe on a complete subset. And tidying means that it's in the format that you want and that makes it easy to work with. Then you typically step on to some exploratory data analysis, where you just sort of look at the data and do some simple properties and sort of adding up, taking averages. If you look at what's called big data, that's often about summarizing data. And then, of course, you want to visualize it and look at the properties and how the different variables are related. And then, in my view, you go on to a predictive model. And predictive models sit on a spectrum where we go from what is typically called machine learning, where we're very little, we're actually using the model as a black box. And we're throwing some model at it, some data at a model and at a procedure, and with some sort of task, learning to predict some data. But we have relatively little control of the internal settings in that model. And then as you go through deep learning and to probabilistic programming, you start taking into account whatever you know about the data set and the structure of the data set. So in deep learning, if you typically work on images, we start looking at how pixels that are close to each other make up sort of a small local region. And first we learn about that local region, and then we learn about gradually larger regions. And in probabilistic programming, you give a full structure, a model that may involve physical mechanisms, physical laws that you can then relate to your data set. A really cool thing is decision theory, where you then go on and say, based on these models, what should I do? Yeah? So you can make the correct choice, or at least the optimal choice, given the data that you have. And then you have some sort of output, and it typically consists of creating reports or creating notebooks, and then sometimes creating a dashboard for your data, and then creating some sort of product or some sort of service that's based on data science. By service, I guess I mean some sort of API you're creating or whatever you're interacting with the consumers. All right, so that's kind of the data flow, except if you're doing notebooks, you'd better add those visualizations to the notebooks. And if you have a dashboard, you probably want some visualization as well. And you want to visualize not just the summaries of your data, but also your clean data. And actually doing visualization is a really good way of diagnosing if these models are accurate and if they're fit for purpose. And let's see, where was I? So this process of cleaning data is often quite laborious, and you can actually use machine learning to help inform that process. Just like you can help visualize the data, the raw data, and try and find outliers. It's a very good way of cleaning data. And of course, you want your clean data to be shown in a raw format as well, often in your dashboard. These summaries as well often want to make it into the reporting notebooks and the dashboards. And actually, your dashboard, if you can explore the data within the dashboard, that's something that can work really well and give a very interactive experience, and you let you explore the data. And one of the cool things you can do with decision theory is, you can decide what's the next. If I want to run an experiment, what's the next experiment I should be running? What's the next thing I should be asking? If you're asking questions of some people, you can say, you can use decision theory based on your models. Say, what questions should I ask of which people? And so pretty soon, your data flow diagram looks like this, which is sadly an accurate architectural diagram of most data science systems, code bases. Okay, and so I didn't just make that up to be funny. There's papers here about the high interest credit card of technical debt in machine learning, arguing that code bases can very quickly become a burden. And so things to avoid or problems are boundary erosion, entanglement, undeclared consumers, and a variety of system-level anti-patterns, which they identify as system-level spaghetti, glue code, pipeline jungles, and configuration debt. Now, so I have a solution. It's not a silver bullet. It's not a full solution, but I have a suggestion, and that is to use Haskell. Why do we use Haskell? So I think Aaron from FP Complete articulated it quite well when he said that Haskell is the only language which is productive. That is, you can get a lot of work done very quickly. The code that you write is fast, and it is precise. We don't mean that by using Haskell we get more significant digits in our calculations, but what we mean is that we can reason precisely about the code that we write. In particular, the type system allows us to say very precisely what does this function do. Well, it's a machine that transforms this kind of data into that kind of data. OK, so for the rest of the talk, I'm going to talk about some packages. So this talk is going to be a bit of a whirlwind, and I wish I should probably have gone instead into depth in 1 or 2 packages. But I picked 4 packages, and I'm going to talk also about some data visualization. But I'm going to talk about, I guess, 5 packages on HaskellX or on GitHub that I've been involved in some of them, but not in others. And they fill this ecosystem, this need for tools. And that is frames and analyze for data frames, FUML for machine learning, Haskell do for reporting notebooks. I should say I have no involvement in this. I wrote this. I wrote -do for dashboards. I kind of wrote the back end against my own knowledge for Haskell.do. And I'm going to talk about some more conceptual stuff in data visualization. OK, so well, data frames are a huge success story. So I guess I should say that. So most data scientists use R or Python, and there's a little bit of a friendly competition going on, and ideas bounce back and forth. A lot of ideas come from R and then get implemented in Python, because more people know Python. And it's a little bit of a cleaner language. So data frames coming from R and then pandas in Python are a common way to represent a range of data. And you should probably think of it as something that's isomorphic to a list of records, some kind of spreadsheet data, where you have named headers, and then you have some columns of data going down. A key thing about data frames and in Pandas implementation is that you can have more stuff in a data frame than you can fit in memory. So you can either just load it all into memory, so it's just some sort of list, literally a list of records, or sometimes the other way, a list of columns. But you can also have it streaming on disk. So whatever operations you do, just at the end of the day, get rolled up, and then you process that streaming from disk in constant space. And the kinds of operations you want to do are sort of what you might imagine you could do with spreadsheet data. You want to filter, map, transform, slice, dice, project the columns, etc. OK, so there are 2 packages for this in Haskell. And one is frames. And it's based on Vinyl, the Vinyl record library. And so it's been around for some time, as has Vinyl. And so it uses template Haskell to generate your types for you. So you make a top-level template Haskell call like this. And so it will, in template Haskell, inspect your CSV file. And it will generate the data types that it thinks corresponds to the rows in this file. And so you don't really see this user type. And look, I don't really like that, but I don't think that's tragic, because you could always just define your own type and then instead write some code that reads this type. So it's meant to be done as a convenience, that you don't have to define your own type, but you can just read it from, you can generate it from whatever's in the file. So I think that's even useful for some cases, although it's not what I would do. And so they've done the full in-memory thing. So they have different representations. They have in-memory or streaming. So you can define it either as a vector of rows, or you can define it as a pipe of rows, and you can do the operations on that. And these you can have quite diverse columns. But so the problem that I have, the larger problem is that, as far as I understand it, vinyl is quite inflexible in the way that the fields are defined. And I cannot introduce an operation where I transform the type of one field from one type to another. So I cannot have, so the map operation is this, right? So I get A to A. I do not have A to B. And I think that's really a shame, because you may start with some doubles, and then you want to introduce a Boolean based on whether this double is greater than 40 or whatever. And so because in vinyl, the records are not truly anonymous, they're defined at the top level, as I understand it, there's a kind of inflexibility here. So the other package is completely the opposite. The other package is very untyped. And so in analyze, it's actually, I've simplified it slightly, but this is what it is in essence. So a frame here is just a list of keys, which is probably what these is some sort of string or something. And then you have your data, and that's just a vector of vectors, so a vector of the rows. And they all have the same underlying type. And this can be doubles, this can be strings, or it can be some sort of union type where you have either double or a string. And I think you can, after you've made this definition, everything else is just very simple Haskell 98 programming. I think you can see how we could do filtering, we could do maps, could do projections, and all sorts of a lot of it comes down to folds. But ultimately, you're sort of stuck with doing only one type, which means that everything has to be a double, or you have to have this untyped approach where everything is a union type. So I want to show an application of data frames that kind of challenges the way that these things are often used in the Haskell community. And that's trying to get what's called tidy data tidying. So there's a formal definition of tidy data. Well, it's not that formal, but so that is that every variable is in its own column, every observation is in its own row, and there's a value in each cell. And often when you get a data set, this is violated. I'll show you here one that's where this doesn't hold true. So here, we've got a small spreadsheet here. And this is sort of the number of cases of some disease in these countries. And in different years. And here it's not the case that every observation is in each row, because these are two different observations, right? So I've made this observation in 2 different years. And so I want to transform this into a data frame where this is the case. So every observation is a row. So I kind of want, so in R, there's this package called tidyr, which defines 2 operations, gather and spread. Spread does the opposite of this, but I'll just show you gather. So what it does is actually something quite weird, right? So it transforms between headers, then become cells, right? So these are 2 headers, and they now become cells. And in spread, you go the other way. So cells become headers. So I think this is a challenge to sort of the Haskell community and people who want to define data frames. So I should say that frames has some limited support for these kinds of operations. So can we have a simple algebra for data tidying, so that these operations can be done, and can something like analyze accommodate different types? So I think what we're going to have because of the Haskell type system, we're going to have separate some data frame implementations that are very typed, and some that are very untyped. And we should have some facility for going back and forth between the 2. I think having that incremental typing could be a really good toolkit to have. Okay, so I'll move on to predictive analytics and what's called machine learning. And so, at least in my view, machine learning is really 4 different tasks. So the bread and butter of machine learning is 4 different tasks, which can be plotted on 2 different axes. If I have continuous data, or really continuous outcomes, and whether I have discrete outcomes, and whether I'm doing supervised learning or unsupervised learning. So this refers to whether my outcomes are things that are continuous, or whether they're Booleans, or maybe integers or discrete classes. And this refers to whether I have labels for my data set. So in supervised learning, I give my algorithm a bunch of data, which has predictors and an outcome. And I say, learn that mapping, so that later I can come with a new predictor, and you can predict me what that outcome should be. In unsupervised learning, I just give the algorithm my data, and I say, here's some data. Figure out what the structure is in this data. Tell me something about the structure in this data. All right. So in regression, this is your classical, like this might be, I don't know, interest rate, and this might be sort of economic growth. You know, things can go up and down. Actually, I'd rather deal with this one first. In classification, I say, here's some data. I have observations here on the x and the y-axis, and I have a label here, which is red, green, or blue. Learn a machine so that I can come with a new point here, and you can tell me whether it's most likely to be red or green. Right? In dimensionality reduction, again, I don't really know the structure, but I have, two observed variables here, x and y. And I want you to tell me what correlates with what the principal axis is here. So here the principal axis goes this way. And so I can actually look at this as a compression algorithm. Because from one point, if I only care about this axis, which I deem to be the most important one, I could reduce 2 points onto 1 point. And it's a lossy, so that's a lossy compression algorithm. In clustering, looking at the same data set as here, I get these points, but I'm expected to figure out how many clusters there are and where they are. So we'd probably fail here and pick 2 clusters unless I tell it that there are 3 clusters. So here would be, I'd expect my algorithm to tell me that there's 1 cluster here and 1 cluster here, and I'd expect to know, where are those clusters. All right, so in R and Python, there are various packages that do this sort of stuff, and there's stuff on HaskellX as well for each of these. But I was interested in how you can sort of unify these. Can we have one common interface that unifies these operations? And so I'm going to suggest one. This is a library that I worked on called FUML. And in FUML, I define a supervisor. And that supervisor takes some data. So I'm using parametric polymorphism to unify these different types of operations. So these type parameters are going to correspond to different things for different machine learning applications. So I am starting with, let's start here. So this is my observed data. So O is the type of observation. And I'm going to learn a predictor. And a predictor is something where I can come with a new set of data, which is a vector of doubles, and get the value that I'm predicting. OK, so let's see what some of these are. So M is the monad in which our learning occurs. Our prediction always has to be a pure function, but sometimes you have sometimes you need some randomness, sometimes you need some I/O, maybe for some optimization purposes. So different operations run in different monads for the learning. So this is the learning operation, right? The O is the type of observed labels. So for instance, in the regression example from before, I'd observe some continuous outcome, which is a double. And P are some model parameters that are specific to every model. So they will be different for every learning procedure, every learner, every supervisor will have its own P, where it stores its internal parameters. And I could have hidden these, but for practical purposes, you often need to look into these. And that's actually, often that's what you're really interested in. It's not so much learning a black box prediction, but you're interested in what are some of these internal parameters. The predict object, which you're learning, stores that P so you can access it directly. Yeah, that's all to say about that, actually. And then the A parameter here is the type of predicted labels. Now, sometimes that would be the same as the type of observed labels, but that's actually not usually the case. And when you're doing the most correct way of learning, that's not the case. So sometimes I would, I'm working on data that's, so sometimes you want to use the difference between O and A as a, to communicate the uncertainty in your prediction. Okay, so let me see here. So here I have my 4 tasks, and so I can have a table here that tells me what these, how these are differently instantiated for different learning tasks. So for classification, my observed labels are either Booleans or anything that satisfies the equal type class, maybe some sort of, red, green, and blue in a union type. And my observed outcome for regression is a double. For unsupervised learning, there are no labels. Yeah, so this is the unit type. There are no labels here to learn. That's why it's unsupervised. And then A, which is the predicted labels. So this is when I come with a new vector, a new set of predictors. I get this. So if I was originally classifying true and false, I could give you another true and false. Is this more likely to be true or false? But I can also give you a double, and that indicates my confidence that it's a true or false value. So if it's close to 0, it's probably a false. If it's close to 1, it would probably be a true. Again, with regression, I might want to predict a number, but also tell you how confident I am about predicting that. And for clustering, when I come with a new predictor, I want to know which group is it in. For dimensionality reduction, I want to go from a larger vector to a smaller vector, because I'm reducing the dimensionality of this. Let's see a quick example of this. So here I've got my classical linear regression. This is the simplest regression procedure that exists, as far as I'm aware. And it's really a very simple piece of linear algebra. There's an inversion of a matrix and some matrix multiplication. And the result of learning that is a vector of regression coefficients, which are put into my predict module, predict data type. And here's my procedure to make a new prediction. And then I can do my learning here. So here I learn this P here actually has the type. That's the prediction type. Sorry, I should have called it something else. And then I can make a new prediction by giving a new vector and calling the predict function on that. OK, so this is called FUML. I think that stands for functional machine learning. And so we've got some base types in the core package. And then we do support vector machines in the SVM module and neural networks. Both of these for regression and classification. All right, so this is all on GitHub. OK, so I have to whiz through this. I think in notebooks, we're now moving on to showing how this data, showing the output of this process. And so I think just to draw an analogy here. So we're all familiar with literate programming. This is where you invert code and comments, where you write something here. This is like a comment, but you write it without any comment marks. So actually your code is I think these are called bird tracks. The code is sort of put in a comment, so it sort of focuses more on reading it rather than letting computers execute the code. And so this has been around forever. And so moving on to notebooks. The dynamic reports. I add to literate programming another capability, and that's the possibility of asking a question. Yeah, so I can ask a question here, and then this code is evaluated, and when I typeset this report, I get the answer, and this answer can be text, but it can also be plots and graphs and whatever else you want, whatever you can in some systems, whatever you can render to HTML. And so we actually had this ability in LHS to Tech. In LHS to Tech, you can evaluate code. And then moving on to graphical user interfaces, we can, we have a little bit of a GUI on top of this. These go in boxes, and there's some evaluation here going on. I'm going to skip showing one of these. Sorry, design. This is the state of the art, and we have iHaskell as well, and then we have Haskell Do, which I'll skip showing here. But these are some of the things we'd like that we don't always have. So first of all, we want good error messages. I'd like to be able to run this code in any underlying monad. So I'm actually surprised that in GHCI, I can't choose the monad I'm running in. Right? I don't know why that is. Why can I not choose my monad in GHCI? I'm completely unable to change it, but what if I want to have some reader monad with a database connection? I'd like to be able to do computations inside that. And then long computations, I'd like to cache so that I don't have to redo them every time I render. And then tracking dependencies. Let me show you how this works. Let's say I have a cell and I write x equals 2, and then I ask what's x plus 2, and the answer is 4. And then later I change this cell, I change it to 3, and lo and behold, now this still says x plus 2 equals 4, because there's no dependency tracking between the two. And this is the case in IPython. Yeah? So in IPython, you can get this state. So you have to reevaluate everything to resolve that. And that's unsatisfactory. OK, let me move on to dashboards. This is where you have a more interactive web front end or some other kind of front end where you can explore the data and more focus on visualization and no showing of code. So the state of the art for dashboards is a package for R called Shiny, which is a framework for creating these small web applications based on data analyses, and these are sort of interactive. So you don't. The great thing about Shiny is it's made for data scientists. So you don't at all talk about a whole bunch of stuff that we talk about when we create web applications normally. So we never talk about routes, form parsing, page headers, or any kind of submit cycle. But all you do is link form elements to state variables. And then you specify a function that calculates the display based on those state variables. So I started working on an implementation of this in Haskell, a port of these ideas. So I used the Lucid library to wrap an HTML generating computation, but with an inner monad where we can do stuff, and this might be I/O, so I can access databases. And then I wrap this up into an object that I can then run. So this is a this is a value of a dashboard, and I can run that by interacting with a web server. I'm going to show an example of this, but the kind of example, the way so everything is parametric on a type, which is the type of your display, and you link values in that type through a lens with the form elements, which each have a specific type. So numeric variables will have a double or an int, or is polymorphic over anything in num. And so you create these values by using this, but also using all the Lucid combinators for creating HTML. I think I will show an example of this, but I want to just go on to data visualization because I think this is really important. And despite the fact that it's become more prevalent and people recognize that it is very important, it's still not important enough. And there's a very impressive system here called the grammar of graphics, which is implemented in R in a package called ggplot, where instead of just having a sort of standard plot combinators like scatter plots and bar charts, you compose your plot by tying together aesthetics, which map variables to dimensions, then using geometries to interpret those, and then going all the way up to a finalized plot. So it's like a pipeline. And so here's an example of that. And this is one of my favorite examples. It always kind of makes me laugh. So this is looking at some data, which is in this variable. That's a field in this data set. And so this is a bar chart in polar coordinates. Yeah, so I'm adding the bar chart geometry to the polar coordinate system. So what do you think a bar chart in polar coordinates is? Any ideas? It's a pie chart. So even if pie charts are not built into the grammar of graphics, you can compose them in this way. And I think I really encourage, if anyone who's out there who's maybe a PhD student and they're a little bit bored on working on, formal process calculi verification or calculating compilers or something like that, I'd encourage anyone from the theoretical science community to look into this grammar of graphics and think about what can we do with, how can we formalize this in a type system and in a slightly less in a more typed approach. And I think that there's a lot of work here that could be done, and not just about typing things and preventing you from shooting yourself in the foot, but I think as this demonstrates, come up with new ways of visualizing things. Yeah, so I think I encourage anyone to look into that. But I want to go a little bit further here. I want to talk about what I call the grammar of interactive graphics. And so this is about not just composing plots, but also looking at different ways in which those can be interactive. So here's one of my favorite examples. This is the dc.js library. I did not write this, and I often demonstrate it. So this is a plot of the NASDAQ 100 price movements. And it's like a standard visualization. But the key thing about this is that everything here is clickable, and everything will lead to a new state of the visualization. So if I'm interested in how the NASDAQ did in Q2, I click on this plot, and now everything drills down to Q2. And if I'm only interested in Tuesdays, again, now I'm just looking at Tuesdays in Q2. And I can go even further down into a year. Yeah? So now I'm in 2002, Q2, 2000 on Tuesdays. And so I can do this in any order that I like. So if I'm interested in a different year, I can do that. So I can look at only the gains. So I think this is very impressive. And so we started looking at how can we support this in -do. In fact, -do was designed from the beginning to support this this way of creating interactive dashboards. And so here is a visualization of the Gapminder data set. So this is a data set about GDP and life expectancy over the years in different countries. And so here I get, unfortunately, you can't see everything, but this, here we go. So this is over time. So this is now the average for all countries. But I can drill in, and I can now look at only life expectancy, how that changes over the years for America, for the Americas. And I can click on one of these, and then I drill into just that country, just what was that? Just Honduras. And I can do this in any order I want, actually. So you can see, you can look at how some of these countries the life expectancy decreased. So I think I have a problem here with, it seems to not quite click at the one I wanted to click at. So here, life expectancy went down in Swaziland. So it's kind of interesting. And so you can explore this data set in different ways. And so this is not a lot of code. Well, there's a certain amount of definitions of these plots. So these plots are, this is the code to define the plots. But linking all this up for all that data, all of it, which is also there's also a table down here, is is actually not that much, and then this is all typed. So what we did here was when you click this pie chart, a donut chart, that's tied into a state variable in the visualization. That state variable is here. So here, when you select countries or select continents, that text becomes non-empty, and just by clicking that element. Right. Okay, so much I haven't had time to talk about. There are packages now in Haskell on HaskellX for a lot of these tasks. So Foldel, one of my favorites for summarizing data sets and calculating statistics. Several data visualization packages. Some of them are based on diagrams, and a lot of efforts to build plots on top of diagrams. HLearn was an early package for machine learning. It's kind of it had a different focus than FUML, sort of focusing on streaming models in a certain sense. Now a couple of packages that focus on deep learning in Haskell, so bindings to TensorFlow, but also a pure Haskell library that's dependently typed. And probabilistic programming, where you build explicit statistical models. Several efforts here: declarative, Hakaru are academic efforts, and declarative is for doing Markov chain Monte Carlo. And there is also a IPython kernel for Haskell. Right, I think that's pretty much it. So the Haskell ecosystem for data science is no longer non-existent. That's great. But I think also, looking at these packages that we do miss, and that where there's still some work to be done. Of course, there's work in terms of translating this, but there's also an opportunity to recast data science in our own vision and turn it into not a Jackson Pollock, but a bit more of a Mondrian picture. Thank you.
Any questions?
Yeah. Okay. Right. Good question. So it is all on GitHub, and so I have this mono repo which has a lot of projects together. So it's diffusion kinetics open. But I'll probably put some of these on HaskellX, so you can just search for -do and FUML on HaskellX, and then they will link to this page. But that example that I showed you here is here. So it's this gapminder scatter plot here. Oh, sorry. All right, I seem to have some sort of. Okay, sorry. Right. So here we go. This is the mono repo, and do you want a? So that example with the gapminder is here, and it should just compile, and all these things have stack files.
So basically, all of your work you're doing, or all of the data science work that you do it with in Haskell?
Yeah, I tried to. No, well, okay. So to answer that, I tried to do some Python because I felt I'm just a joke data scientist who doesn't know Python, and I tried. I really tried. I just can't stand it. I really can't. I just. But there is this for probabilistic modeling. Actually, I use this package called Stan. So it's a domain-specific language for building probabilistic models, and actually I didn't link it here. I have a interface to that also in this repo. There's a Haskell interface to Stan, so you can interact with the two. Yeah, I tried F#. That was awful as well. Actually, so the interesting in the Haskell ecosystem for data science is much better than F#, which was a surprise, a huge surprise, but it is.
Then you have plenty of time to speak to the speaker at having lunch, and again a big applause for the speaker.